SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be deriving how we can find the linear form of the moment equation along y-axis, because the moment along y-axis actually generates the desired pitch angle that control the pitch angle. Now, let me rewrite the linear form of the forces along x and g direction. Then we'll start the how we can find the linear model of the moment equation along y-axis. Rewriting the force, the linear forms of force equation in x and y direction in the longitudinal equation of motion of aircraft so linear form of the equation. In the x direction we had d by dt minus xu delta u minus xu delta w plus g del theta cos theta naught equal to x delta e del e plus x del t delta t. Let me define this equation number 1, and the linear form of the force equation along g direction we can write minus zu del u delta u plus 1 minus w dot d dt minus zw delta w minus zq plus u naught del t dt minus z sin theta naught delta theta equal to z delta e capital delta d plus z delta t capital delta dt. And let us define this as equation number 2. So if you notice, this equation number 1 and 2 are linear form of the forces along x and g direction. Now we'll find the linear form of the moment equation along y direction. So where we are going to control the pitch rate of the y-axis. So finally, considering the third longitudinal equation for P equal to R equal to 0. So here only we are looking at the pitch rate along y direction. So we can write for this condition. So here basically this is the linear form of the equation, the linear form of the forces along x and z direction. Now we are going to find the linear form of the moment equation in the longitudinal motion. So for this condition P and R equal to 0, we can write the moment equation MP equal to IY Q dot. If we take this condition, our moment equation along P y-axis will be reduced to this form. This is Y, IY, moment of inertia along y-axis. Following the same procedure, of including the perturbations variable, we get perturbation variables. Here we're gonna consider along MP moment equal to, we can write MP trim value and the perturbation in moment delta MP we can write, and the pitch rate Q equal to Q naught plus del Q, we can write this expression. And using this part of variables, we can write the equation. We write this equation number 3. We get equation number 3 as MP naught plus delta MP equal to IY d dt Q naught plus delta Q. And for steady state trim flight condition, already we have, if you remember, we had the equation for the steady state condition. For the steady state trim flight, we had MP equal to 0 and Q not equal to 0. This already we had before. This condition for the, this is basically the trim condition for the longitudinal motion of the aircraft. So for this condition, equation number 4 yields to be delta MP equal to IY delta Q dot. And here, this is the equation is written in the part of variable form. And so here, delta MP basically the total moment, part of moment acting on the y-axis due to the different variable in the system. This moment generates due to the different variables in the system. So let's see how we can write the Taylor series expansion of the delta MP where the different variables comes into picture. Let me write delta MP equal to, we can write function of delta U, delta W, delta Q, delta del E, delta del T. So these are the variables which generates the part of moment in the y-axis, or if you write in Taylor series expansion, we can write delta MP, delta U, del U, plus delta MP delta W, capital delta W, delta MP del MP del W dot delta capital delta W dot plus del MP by del Q delta Q plus del MP by small d delta E, so del delta E capital delta del E plus del MP divided by del small delta T capital delta T. This is the equation which has been written in terms of Taylor series. Now, if you substitute this delta, capital delta MP, this is equation number, equation 4, 5, equation 5. Now, substitute equation 5 in equation 4, we can write substituting equation 5 in equation 4 else we can write delta Q dot equal to 1 upon IY del MP del U delta U plus del MP per del W delta W plus del MP del double dot delta double dot plus del MP del cube del Q delta Q plus del MP del delta E capital delta E plus del MP del delta T capital delta T. So this is the equation for moment equation in part of variable form. Let me define this equation number 6. Now denoting mu as 1 upon IY del MP delta U and so on, which are basically are the aerodynamic derivatives divided by IY. And these derivatives generally we find for the given flight condition, and we can derive these values for the wind tunnel testing. Now, again, if you consider again, we know that del delta theta dot, and using this stability derivatives and using this expression, using the stability derivatives, equation 6, we can write equation 6 can be written as minus mu delta U mw capital W minus m w dot d dt capital delta W minus mq d dt delta theta plus d square dt square delta theta equal to m delta E, capital delta E plus m delta T, capital delta del T. And if we further simplify this expression, we can write minus mu delta U minus m w dot d dt plus mw delta w plus d square dt square minus mq d dt capital delta theta equal to m delta E, capital delta E plus m delta T, capital delta T. And let us define this equation by equation 7. Now combining equation 1, 2, and 7. So if you notice this equation is written in linear form. And here we have another set of linear equations, which are equation 1 and 2. So combining 1 and 2, equation 7, we can come up with the state space form. So let me write one small note. The longitudinal, the linearized equation of motion defined by equations 1, 2, and 7 for the longitudinal aircraft motion are simply OD form, ordinary differential equation with constant coefficients. So it means the equation also time invariant, because as per the property of time invariant, the coefficient of the equation does not vary with time. So this system also you can say linear time invariant system or LTI system. Let me write these coefficients are made of aerodynamic instability derivatives which are mass and inertia characteristic of the aircraft. This equation, the equation 1, 2, and 7 can be written as in state space form we can write in this form x dot equal to ax plus bu. Here x is the state vector and u is the control vector, which will be designed through the control algorithm, which will provide the desired control input to the system, and x can be propagated. So here matrices A and B contains the stability derivatives. Now, let's look further how we can find the state space form in this form x dot equal to ax plus bu form. Let's look from equation 1. Equation 1 is here. From equation 1, we can come up on delta u dot form. From equation 1, we can write delta u dot equal to xu capital delta u plus xw capital delta w minus g cos theta naught capital delta theta plus x del e delta del e plus x delta t delta t. And again, it should be noted that in equation, there are one more assumption we have to consider in equation 2. In equation 2, the force derivatives, which are zq and zw dot, this expression zw dot and zq are usually are neglected since their contribution is very minimal in the aircraft response. So we can write further the derivatives zq and zw dot in practice usually neglected since their contribution is very minimal in the aircraft response. Hence, equation 2 can be written as capital delta W dot, the rate of change of velocity in z direction. We can write ZU capital delta U plus ZW delta W plus U naught delta Q minus G sin theta naught delta theta plus Z delta E plus Z delta T capital delta T. And let us define this equation number 8. Sorry, let's define this equation number 8, and this is equation number 9. Equation 7 here. Equation 7, this equation 7 can be written as minus mu, the moment equation, and delta u minus mw dot delta double dot minus mw delta w plus delta theta double dot minus mq delta theta dot equal to m delta e delta e plus m delta t capital delta t. Let us define equation number 10. And also we know that the rate of change of angle theta is equal to delta q. So again, by using delta q delta theta dot, or we can write delta q dot equal to delta theta dot. And incorporating this thing in equation 10 10 can be written as and delta q dot equal to mu delta u plus mw dot delta w dot plus mw delta w plus mq theta dot plus m delta e plus m delta t capital delta T. And let's define, this is equation number 11. If you substitute equation 9, this expression, in equation 11 in place of delta w dot, we can further write, so in substituting equation 9 in equation 11 yields, we can write delta q dot equal to mu plus mw dot zu delta u plus mw plus w dot zw delta W plus MQ plus MW dot U naught delta Q minus MW dot G sine theta naught delta theta and plus M delta E plus MW dot J delta E delta D plus M delta T plus W dot J delta T delta dt. And this is the final moment equation, linear moment equation. Here we are having the nice form for delta U dot. This is delta U dot. Delta U dot, delta W dot, and delta Q dot. Also, we need to consider delta this expression, because how the angle going to change with respect to pitch rate. So we are having four equation. One equation delta U dot, delta W dot, delta theta dot, and delta Q dot. So we can now write the state space form x dot equal to x plus bu form. Let's start writing. Okay, let's define this equation number 12. So equation, and this is, let's define equation number, equation 13. Equation 8, equation 9, equation 12 and 13, if we write in compact form, finally, writing equation, writing the longitudinal equations 8, 9, 12, 13, 8, 9, 8, 9, 12, and 13 in state space form. We have state vector here, del U dot, del W dot, del U dot, and del theta dot. So four variable needs to be controlled, and our A matrix we can come up XU. Just we have to consider the coefficient of delta U, XW 0 minus G cos theta naught, and from delta W dot equation, the coefficient of ZU, ZW, U naught minus G sine theta naught. And from delta Q dot equation, we have the coefficient of the state variable mu plus mw dot ZU mw plus mw dot ZW mq plus mw dot u naught and minus mw dot g sine theta naught. And delta theta dot expression equation number 13, we have 0, 0, 1, 0. And the state vector are delta u, delta w, delta q, and delta theta. This is the state vector, and this is the state matrix, we can say. And the control matrix, the coefficient of delta, capital delta delta t, and capital delta delta e. So if you write the control matrix for delta u, x delta e, x delta t, z delta e, z delta t, m delta e plus m w dot delta e, m delta t plus m w dot dt delta t, and 0, 0. And the control vector are delta delta e and delta delta t. So this is our control matrix. This is A matrix, this is B matrix, this is U vector, this is state vector x, and this is x dot. So this expression we can write in compact form, x dot equal to ax plus bu. And so basically, if you write the control block diagram, we have, this is our reference point where x dgr basically the dgr value of u, w, q, theta. So this is the linear system. So here you can say that in a dgr. So for example, if you consider 0, 0, 0, so we can, because these are the basically part of variable, so we can assume the dgr values should be 0, 0. So here we are having the control algorithm, basically controller, which gives the dgr control input to the plant. This is x dot equal to ax plus bu, and this is our actual output x, and through feedback we can, suppose this is feedback path, feedback, and we have this is the output tracked by feedback element, and this is negative, this is positive. So we can, if you say this is our GP plant, this is GC controller, this is h of s, this is basically how the, this is how the control system, closed loop control system, can be designed to control the desired value or the pattern value delta u, delta w, delta q, delta theta. And this is the linearized model of the longitudinal equation of motion, states linearized state space model of longitudinal equation of motion of the aircraft. So let's stop it here. From the next lecture, how we'll continue to find the linearized model of the lateral directional motion of the aircraft. Thank you.